Do you dare to look down? Imagine yourself driving a vehicle suspended 625 meters above the valley floor. To put that into perspective, if you were to drop a stone from this height, it would take nearly 12 seconds of terrifying freefall before it finally broke the surface of the river below. You are currently positioned higher than 2 entire Eiffel Towers stacked vertically on top of each other and well above the observation deck of the Empire State Building. At this dizzying altitude, you are not merely traversing mountain peaks, you are flying directly through the clouds. Welcome to the Huajiang Grand Canyon Bridge, the engineering marvel that has officially claimed the title of the highest bridge on our planet. This is not a scene from a high-budget science fiction film. It is the most audacious, gravity-defying feat of civil engineering ever realized by human hands in southwestern China. Today, we will explore how visionary engineers suspended a multi-lane highway in the sky, overcoming extreme natural elements and geological nightmares to redefine the limits of infrastructure. We will look beyond the steel and concrete to understand the sheer human will that drove this project from a seemingly impossible blueprint into a monumental reality. Before the first ounce of concrete was poured, engineers had to confront the brutal reality of the terrain. The bridge is located in Guizhou province, a region in southwestern China that is widely regarded as a geological nightmare for transportation planners, yet a paradise for bridge builders. With over 92% of its total land area composed of rugged mountains, steep hills, and elevated plateaus, Guizhou is the only province in China that contains no flat plains. The entire surface of this territory appears as if it was violently torn apart by tectonic forces, leaving behind thousands of deep, vertical canyons and raging rivers. Historically, this fractured landscape isolated communities, turning short journeys into multi-day treks. This extreme topography is precisely why Guizhou has earned the title of the world's Museum of Bridges. Out of the 10 highest bridges currently standing on our planet, more than half are located right here. However, even by the extraordinary standards of this region, the Huajiang Grand Canyon Bridge project presented a structural challenge on an entirely different level, pushing modern construction techniques into uncharted territory. The primary obstacle for this project is the formidable Huajiang Gorge, carved over millennia by the powerful Beipan River. This gorge is often described as a dramatic scar on the face of the earth, featuring sheer limestone cliffs that plunge straight down into the abyss. The canyon is constantly cloaked in a dense, unpredictable layer of mountain fog that limits visibility to near zero. Furthermore, the wind here does not behave according to normal atmospheric patterns. Instead, it is funneled through the narrow, high-walled gorge, accelerating into violent, unpredictable vortexes that can easily reach speeds of up to Category 14 storms. These localized gales possess enough force to easily overturn heavy commercial trucks. For generations, this deep chasm meant the residents of the opposing counties of Luxi and Anlong had to endure a grueling 3-hour journey along dangerous, winding mountain paths just to cross to the other side. A bridge would reduce this travel time to a mere 60 seconds. But how do you construct a path across a 1,420-meter void suspended half a kilometer in the air when the wind is trying to tear you down? To bridge this massive chasm, engineers carefully evaluated 3 classical bridge designs. The first option was a traditional beam bridge, which is highly reliable and common. However, to support a beam bridge over this deep canyon, they would have to construct concrete piers rising over 600 meters from the riverbed below, a feat that is both technically impossible and financially ruinous. The second option was an arch bridge, known for its elegant aesthetics and high structural stability. Yet, a 1,420-meter span is far too wide for a single concrete arch, and the highly weathered limestone cliffs on either side lacked the lateral load-bearing capacity to withstand the immense horizontal thrust of such a massive arch design. This left them with the third and final option: a super-long-span suspension bridge. This design would allow the highway to leap across the entire canyon in a single, continuous bound without placing a single support pier in the deep riverbed. However, selecting a suspension bridge meant facing a brand new engineering riddle. How do you safely anchor a steel highway weighing tens of thousands of tons using only 2 main cables? Before the bridge could reach into the sky, it had to be firmly anchored into the earth. However, in Guizhou, the ground is highly deceptive. Although the visible limestone cliffs appear as solid and durable as steel, the reality beneath the surface is a chaotic karst network. This geological formation is notorious for its highly weathered rock, deep fractures, and most dangerously, massive subterranean caves filled with pressurized groundwater. Attempting to place a massive concrete tower weighing hundreds of thousands of tons on this hollow, unpredictable ground is the structural equivalent of balancing a heavy steel weight on a fragile eggshell. If the foundation shifts or settles by even a few centimeters, the entire bridge structure would experience severe twisting forces, leading to a catastrophic structural failure. To overcome this hidden hazard, engineers had to look deep beneath the surface, treating the mountain not as a simple platform, but as a complex, dynamic system that required a highly specialized foundation design to ensure absolute long-term stability. To secure the bridge against geological movement, engineers decided against placing a standard shallow foundation on the surface. Instead, they literally sewed the foundation deep into the stable core of the mountain. At the location of Tower Number 6 on the Anlong side, construction crews utilized massive rotary drilling rigs to excavate 24 deep vertical shafts. Each of these bored piles boasts an exceptionally large diameter, penetrating deep through the weak, weathered surface limestone to reach the solid, uncompromised bedrock deep within the mountain's core. Once these deep shafts were cleared, they were reinforced with dense cages of high-strength steel rebar and filled with thousands of tons of high-performance concrete. This created 24 massive, monolithic concrete roots that firmly lock the entire tower foundation into the stable mountain structure. This deep pile design ensures that even if the outer layers of the cliff erode or experience minor localized slides over the next century, the main tower will remain perfectly level and completely unaffected. With the deep foundation securely anchored, the two main concrete towers began their rapid ascent into the sky. The Luchi Tower on the northern bank rises to a height of 205 meters, while the Anlong Tower on the southern bank reaches an astonishing 262 meters. To help visualize this scale, the Anlong Tower alone stands as tall as an 80-story skyscraper. Constructing these colossal concrete structures on the edge of a windy, vertical cliff presented extreme safety and logistical challenges. To build them safely, engineers deployed advanced hydraulic self-climbing formwork systems. This technology acts like a mobile, automated factory that wraps around the tower's perimeter. After a concrete segment of 4 to 6 meters is poured and cured, the integrated hydraulic jacks automatically lift the entire scaffolding and formwork assembly upward to prepare for the next pour. This highly automated process operated continuously, allowing the massive concrete towers to grow at an impressive average rate of over 1 meter every single day. Height alone is not enough. These massive towers must also possess incredible lateral strength to withstand the extreme environmental forces of the gorge. Between the two vertical legs of each tower, engineers designed and constructed massive reinforced concrete crossbeams. These crossbeams act as structural braces, tying the tower legs together into a rigid, unified frame. This configuration functions like a giant skeletal system, distributing lateral wind loads and seismic forces evenly across the entire foundation. This design is critical because the towers must not only support the downward weight of the bridge deck, but they must also resist the continuous, violent buffeting of the canyon's Category 14 winds. By connecting the tower legs with these high-strength crossbeams, the engineers ensured that the towers can flex slightly under extreme loads without cracking, providing the necessary structural resilience to survive major earthquakes and the most violent superstorms that are projected to hit the region over the next century. To understand how a suspension bridge works, imagine a giant hammock. The two main towers act as the trees supporting the hammock, but what keeps these towers from collapsing inward under your weight? It is the high-tension cables anchored firmly into the ground at both ends. On the Huajiang Bridge, the tension pulling on the main cables is immense, reaching tens of thousands of tons. Without a highly secure anchorage system, the 262-meter concrete towers would be pulled inward and collapse into the gorge. On the Luchi side, where the terrain is relatively flat and stable, engineers utilized a massive gravity anchorage design. Concept is straightforward. To resist a massive pulling force, you need an even heavier block of concrete. Crews excavated a colossal pit and filled it with 164,000 cubic meters of dense concrete. This single block weighs more than 35,000 average vehicles, utilizing its sheer dead weight to lock the main cables in place, easily resisting any forces exerted by the bridge. On the Anlong side of the gorge, the steep 45-degree cliff face made a massive gravity anchorage impossible. Excavating a massive pit here would have triggered catastrophic landslides and devastated the pristine mountain ecosystem. To solve this, Chinese engineers deployed a highly elegant tunnel anchorage design. Instead of building a massive concrete block on the surface, they chose to use the natural strength of the mountain itself. Crews excavated 2 deep tunnels extending 90 meters into the solid rock at a steep 45-degree angle. The tunnels were designed with a flared, wedge-like shape at the bottom. Once the high-strength steel cable strands were routed to the very bottom of these shafts, the entire tunnel was backfilled with high-density concrete. Because of the flared shape, any pulling force from the bridge cables actually wedged the concrete plug tighter against the solid rock walls of the mountain. To pull this anchor out, the bridge would literally have to rip the entire mountain apart. A brilliant display of working with nature. With the towers and anchorages complete, the engineers faced a classic suspension bridge challenge: how to establish the very first physical connection across the 1,420-meter void. In the past, engineers had to use helicopters, pilot boats, or even rocket-propelled lines to carry the first guide rope across. For the Huajiang Bridge, engineers turned to cutting-edge 21st-century technology. They deployed a highly specialized heavy-payload drone. This unmanned aerial vehicle took off from the Luchi Tower, carrying a high-strength, ultra-lightweight pilot line made of advanced synthetic polymer. Fighting against the turbulent, unpredictable crosswinds of the canyon, the drone successfully navigated the vast void, landing precisely on the opposite Anlong Tower. This single, thin thread established the initial physical link between the two sides. From this pilot line, crews were able to pull progressively thicker and heavier steel wire ropes across the canyon, slowly building up the tension capacity required to construct the temporary catwalks. Using the pilot lines, engineers constructed the catwalk, a temporary suspended walkway that mirrors the path of the future main cables. Suspended 625 meters above the canyon floor, this catwalk is constructed from lightweight steel mesh, allowing the violent winds to pass directly through rather than catching the structure like a sail. Working on this catwalk is certainly not for the faint of heart. With the wind howling through the metal mesh beneath their boots, workers are suspended in the open air, with the Baipan River appearing as a tiny, winding thread of jade far below. Despite the extreme heights and swaying motion, these courageous ironworkers walked this path daily, installing monitoring equipment, adjusting cable guides, and preparing the system for the main cable spinning process. Their bravery and focus under these extreme high-altitude conditions were absolutely vital to ensuring that the main structural elements of the bridge were aligned with millimeter-level precision. The main cables of a suspension bridge are not solid steel bars. Instead, they are composed of thousands of individual high-strength steel wires woven tightly together. For the Huajiang Bridge, each of the 2 main cables is constructed from 217 individual cable strands, with each strand containing 91 high-strength galvanized steel wires. The total weight of this massive cable system exceeds 9,000 tons. To construct these giant cables, engineers utilized the advanced prefabricated parallel wire strands, or PPWS method. These strands were manufactured with extreme precision under controlled factory conditions, then transported to the site and pulled across the canyon using a high-speed, automated winching system. This method significantly reduced on-site construction time and ensured that each individual wire shared the immense tension load of the bridge equally, preventing localized stress concentrations that could lead to premature cable failure. The greatest challenge when installing these massive cables is achieving perfect, uniform tension across all 217 strands. If some strands are tighter than others, they will bear an uneven share of the bridge's weight, which could lead to individual wire failures and a dangerous chain reaction. To prevent this, engineers performed the critical calibration work exclusively at night. Between midnight and dawn, the mountain temperatures stabilize and the distorting effects of direct solar heating are eliminated. Using high-precision laser rangefinders, GPS sensors, and digital tension meters, engineering teams measured the sag of each individual strand with extreme accuracy. They adjusted the tension of each cable strand to ensure that the entire system was aligned within an incredibly tight margin of error of less than 2 millimeters. This meticulous midnight calibration process was repeated for weeks, ensuring the structural integrity of the bridge's primary load-bearing system. With the main cables fully tensioned and calibrated, it was time to install the road deck. The deck of the Huajiang Bridge is composed of 93 massive steel truss segments, each weighing up to several hundred tons. Because of the extreme height and rugged terrain, these massive segments could not be lifted from the river below using standard cranes. Instead, engineers deployed a highly specialized cable-running gantry crane system that rides directly on the main suspension cables. This advanced machine lifted each steel segment from the assembly yards on the cliff edges, carried it out over the vast void, and lowered it precisely into position. During this phase, the canyon's unpredictable winds were the #1 hazard. A sudden gust could turn a 100-ton steel segment into a massive, uncontrollable pendulum. To mitigate this risk, crews operated during precise early morning weather windows, using high-tension guidelines to carefully stabilize and align each segment before securing it. At an altitude of over 600 meters, the bridge is subjected to a unique physical phenomenon known as the chimney effect. Because the Huajiang Gorge is a narrow, V-shaped canyon, when the sun heats the air at the bottom of the gorge, this warm air rises rapidly, compressed by the narrow walls, creating powerful upward wind currents. To prevent these violent upward forces from destabilizing the bridge, the deck was designed with advanced aerodynamic principles. Instead of a standard solid box girder, the Huajiang Bridge utilizes an open steel truss design with a highly aerodynamic cross-section. The outer edges of the deck are fitted with sharp wind fairings, similar to an inverted airplane wing. This shape allows the powerful winds to flow smoothly around and through the structure, generating downward stabilizing forces rather than dangerous lift. This advanced design was refined through thousands of hours of wind tunnel testing, ensuring the bridge remains completely stable even in the face of extreme typhoons. The Huajiang Grand Canyon Bridge is not merely a passive structure of concrete and steel. In the era of Industry 4, it functions as a highly intelligent, living organism. Engineers integrated an advanced structural health monitoring, or SHM, system directly into the bridge. This system acts like a digital nervous system, featuring over 400 high-tech sensors embedded throughout the structure. These sensors continuously monitor structural parameters in real time, including wind speeds, tower oscillation, cable tension, temperature expansion, and even microfractures, invisible to the human eye. This data is transmitted via a high-speed fiber optic network to a centralized control center where a real-time digital twin of the bridge is maintained. If a severe storm causes a cable to experience unusual stress or a bolt to loosen, the system immediately alerts maintenance engineers, allowing them to address potential issues long before they become safety hazards, ensuring a lifespan of over 100 years. Behind these incredible engineering achievements are the stories of the extraordinary people who built it. The construction workers of the Huajiang Bridge are a unique breed, often referred to as the cloud hunters. Working at heights of over 600 meters, they operate in a highly unusual microclimate. On some days, while heavy rain falls on the valley floor below, these workers are bathed in bright sunshine above a vast sea of white clouds. On other mornings, the fog is so thick that workers cannot see their colleagues standing just 5 meters away, forcing them to rely entirely on radio communication. The psychological pressure of working in this extreme environment is intense. One veteran ironworker shared that during his first week on the high-altitude catwalk, the sheer height and howling wind made his legs shake so violently he could barely stand. Yet, through absolute focus, mutual trust, and rigorous safety protocols, these workers spent years living on these cliffs, successfully raising this monument to human ingenuity. The Huajiang Bridge was designed with a dual purpose: to serve as a vital transportation link and to become a world-class tourism destination. At the top of the 262-meter Anlong Tower, engineers constructed an exclusive skybar and observation deck. Visitors can ride a high-speed glass elevator up the side of the tower to enjoy panoramic views of the gorge. Beneath the main road deck, a scenic glass-bottomed walkway has been installed for those seeking an adrenaline rush, alongside plans for the world's highest bungee jumping platform. Beyond tourism, the bridge is a model of environmental sustainability. To produce the 439,000 cubic meters of concrete required for the project, engineers avoided mining natural river sand, which damages local river ecosystems. Instead, they recycled the limestone waste rock excavated from the tunnel anchorages and foundations, crushing it into high-quality manufactured sand. This green concrete technology saved millions of dollars in transport costs while fully preserving the pristine canyon environment. Upon its completion in 2025, the Huajiang Grand Canyon Bridge will officially open to traffic, forever ending the geographic isolation of this rugged region. The historic 3-hour journey across the gorge will be reduced to a single, effortless minute. By connecting the regional G56 expressway, the bridge opens up vital trade routes between the mountainous, landlocked areas of Guizhou and the bustling deep-water ports of southern China and Southeast Asia. This bridge does not merely carry vehicles, it carries the hopes and economic future of millions of residents. From a daring, seemingly impossible blueprint to a monumental reality of steel and concrete, the Huajiang Bridge stands as a powerful testament to human willpower and engineering excellence. It proves that with vision, innovation, and courage, there are no natural barriers that cannot be overcome. The next time you look up at the clouds, Remember that human hands have built a highway right through them, transforming a deep scar on the Earth into a magnificent monument of unity.